The first time these kind of equations were investigated by Diliman in 1956 for the parabolic hyperbolic type equation. He gave an example connected to the movement of the gas in channel zone by process environment, and the movement of the gas inside channel was described by the equation, wave equation, outside by the diffusion equation. In the other side, how we know at the moment and the recent years, a lot of applied problem of some of the problem of mathematical physics, mathematical biology. I can to show some of the example later, and some of the investigation problems reduced to the boundary or initial value problem for the Laudet partial differential equations. What about the Laudet equations? This equation 1 is called Laudet in dimensionally Euclidean domain omega. If the operator R depends on the restriction of the orthogonal function Ux defined on the closed subset omega, measure this triangle less than F. This equation can be Laudet integral, Laudet functional, Laudet Integro-Differential, and others. But this equation is called Laudet differential or Integro-Differential equation if it's contain at least one derivative of somehow solution. It's very simple, easy definition. And very important here, Laudet equations is especially with applying problems, if it's possible to write in the form of AU equal to LU plus MU. LU is the integral, LU is the partial differential operator. MU, the next part, may be included integral or Integro-Differential form, or the function restriction of the function of U at X. It's the second part is the Laudet part. For example, a lot of researchers confirming the actuality of the Laudet differential equation. For example, phenomenon in complex evolutionary system with memory essentially depending on the prehistory of the system. And this phenomenon is described by the following elliptic type equation or the following parabolic type equation. This is delta is the Laplace operator. This is the main part as partial differential operator. The next part is the Laudet. Here is the Ux tau. Tau is divided from 0 to t. Order this one, the parabolic partial Laudet partial differential equation. And also the following Laudet partial differential equation is found theory of wave propagation in dispersed environment. U is the density. And next, the following Laudet partial differential equations is modeling of the movement of vehicles on the highway. Px Ty is density of the car in the point X. And this kind of Laudet partial differential equations, very important that main boundary value problems, main initial value problems as formulated for the Laudet partial differential equation, same as for the classical partial differential equation. But for investigating with existence of this kind of Laudet part, we cannot use classical method for the investigation. This kind of classical partial differential equation we cannot use. And also the Laudet partial differential equation is very important in the problem of optimal control and dynamical population. And with other side, this kind of Laudet partial differential equation, if we are formulating classical local boundary or interval problem, they can equivalently reduce for the non-local problem, but for the classical partial differential equation without this Laudet. I would like to note here is one of the example, which is called as the McKendrick and von Forster equation. It describes the closed population with this condition, U0 t equal to this integral form as non-local, as it's connected with others side of the domain or in the inside of the domain, and with this initial condition. This kind, if we are investigating this equation, classical partial differential equation of the first order with this non-local condition, This kind of problems equivalently can be reduced loaded partial differential equation. For example, this kind of. Here is the UAE, as the sum of the point is a given function, UAET, the sum of the function. And we can see a lot of examples for applying problems. And I would like to note another one problems and equivalently reduced to non-local problem for the classical partial differential equation. For example, for this loaded partial differential equation, main part is hyperbolic. The next part is integro-differential part and loaded part, where capital V is integro-differential operator in the sense of Ramanujan. Here is if alpha less than 0 in integral form, alpha is equal to 0 is the function equal to the function of u, and alpha greater than 0, it can possible to write integro-differential form. If we are investigating one of the problem, for example, the problem of dark box for this kind of equation, very simple and classic form. For example, if you are investigating characteristic domain, the problem of dark box, with the condition 3 and 4, it's in the characteristic domain. Capital V is the domain in F2. It's bounded with characteristic AC, and BC is the characteristic in this main part. And with the segment AB, Y equal to 0, if we are searching our solution in the characteristic triangle, such as dark box, this kind of local conditions is given in the line AB is the function of mu of x and the characteristic given function of u and normal. We can equivalently reduce this kind of non-local problem, but for the classical partial differential equation, this kind of. Our problem, local problem for the loaded equation, we can equivalently reduce new kind of problem, but for the this kind of partial differential equation without loaded part. It's very important one of the point. And I can explain our main one of the results. This result is with my PhD student, Babadianova Yıldız. And here let omega 1 be a bounded domain enclosed by the C segment. Respectively, omega 2 is a characteristic triangle bounded by this characteristics wave equation. This one, let it will be omega 1. This is triangle is omega 2. And omega 1 plus omega 2 with this AB, we are denote by omega, all of the domain omega. We are investigating in the domain omega this equation. The following linear loaded integro-differential equation, but mixed type. If y greater than 0, is here is will be 0, and uxx minus uy. Our equation is the parabolic. If y less than 0, this is equal to 0, and our equation is hyperbolic, uxx minus uy. And this is loaded part is consist with included this integro-differential operator in the sense of Riemann-Levy. This is the fractional operator, alpha e greater than 0 integral form, less than 0 is the integro-differential form, and equal to 0, it's a very simple form, is equal to ux0, only this one. And for this, if we denote here, E1, E2, E3, and EK is epsilon 1 from 0 to 1, epsilon 1, epsilon 2, and epsilon n, the point. And from each of the point, we can write our characteristic, parallel of the characteristic BC, E1, E1, E2, E2, and another. And same as in each of the points, we can we can to write our, we can to show our parallel our characteristics graph. Here is E1, B1, E2, B2, and others. And we can to investigate the extension of the problem trichotomy. Extension of the problem trichotomy is different of the problem of trichotomy. We can to give our conditions some of the part of the characteristic domains. It's not of the all of the boundary. We can to give our conditions each part of the characteristic domain, and that's why in this kind of problems it's will be extended our problem of trichotomy and can include the trichotomy problems also. Problem T1, find the function uxy satisfying the following conditions. Uxy is continuous in the closed domain and has continuous derivatives, and first order derivatives continuously glued all of the point of the segment AB. AB is in this line. From this part ux0, this each of the point in here from this part and from this part must be glued, continuous glued conditions here, and except possible point as a point this one, and uxy is the regular solution of the equation 1 in the domain omega and takes the given boundary conditions. Our conditions is given in here in this line u and this line and u, and also for even k is given in this part of the domain E1, E2, E3, and for odd k is a parallel in here B1, B2, B3, B4, and other conditions is given B3 and 4. And where phi and psi is given function at the moment simply smooth function. What we are doing? We must to prove existence and uniqueness of formulating problem. We can to prove existence and uniqueness for the equation 1. This extension of the problem of trichotomy, and we can to receive our results. The first, I would like to know our results. Here is the main result. If the function of uxy in this class and uxy is glued together over all points of the segment AB, except possible as a point, this one, and they can only have discontinuous of the first kind, and satisfy this condition, then the solution uxy of the problem T1 is unique in the domain omega. This theorem we can to prove with using the principle of extremum for the mixed type, for the parabolic hyperbolic type equation, and of course we are using the principle for the integro-differential operator. We can to prove this theorem. Our next result is the theorem of existence. Let our given function as the characteristic phi k and psi k, it satisfies these conditions and these conditions, and moreover, if n is an odd number, satisfies the conditions this one, then there exists a unique solution to the problem T1 in the domain omega. Our main next result is theorem existence. I can very short to describe this theorem, the proving of this theorem. How we know we have not that time. The first, what we are doing, I can to drive only the map of the investigation. The first, from the hyperbolic part. From the hyperbolic part, our equation is described as ux(x) minus uyy. This is 0 from the hyperbolic part, and with this loaded part. What we are doing? We can to write from the hyperbolic part solution of the problem of Cauchy in this form. What about the tau and nu? Tau and nu, from the condition first, we know ux0, ux minus 0 and plus 0, uxy is continuous all of the domain omega, all of the domain omega. That's why in each of the point must be glued continuous condition. That's why ux plus 0 and ux minus 0 is equal. And this function we denote the function of tau of x. And also the first derivatives as given the conditions of the problem uy. And we are denote this one is a nu of x. Tau and nu are now function at the moment. If we can write solution from the hyperbolic part in this form, as it's look like to the D'Alembert form, but with louder part, and from the hyperbolic part with our conditions, we have two conditions for even and for odd k, 3 and 4. We are satisfying these two conditions for the solution. This one. And we can receive integro-differential relation for the function tau, nu, and psi2k for even k, psi2k minus 1 for the odd k. We can receive these two integro-differential relations from the hyperbolic part, from omega 2. From omega 1, from the parabolic part, passing to the limit y equal to 0 from the equation, we can receive from the parabolic part for the function of tau and nu this kind of integral differential relation. We are received system for even k, this one, and with this, we can investigate our system for the function of tau and nu, and we can find the function of tau and nu, these integral differential relations. As this kind of, if we excluding mu at x, we can receive this integral differential equation for the function of tau at x. And this integral differential equation equivalently reduced integral equation type of Fred-Golem, type of Baltaeva, this kind of, with the kernel of K1. K1 is here. If we can see the alpha is less than 0, here we have some singularity, but less than 1. This kind of integral differential equation we can investigate, we can prove existence and uniqueness, and we can find the function of tau at x. If we know tau at x from the system, we can find mu at x. Tau and nu, if we know, we can construct from the hyperbolic part our solution with the solution of the Cauchy problem. This one. If we know tau and nu, we can know the solution from the hyperbolic part. It's well known. And from the parabolic part, if we know tau and nu function, here is the we know function of tau. Here is given with the condition u, and here is given condition u. It's first boundary value problem for the parabolic partial differential equation with loaded part, and we can find our solution from the parabolic part also. And we can construct our solution from the parabolic part as first boundary value problem. And same as we can do our receive our integral differential equation from the for the odd k also, and we can equivalently reduce integral differential equations. This kind of integral differential equation, integral equation type of Baltaeva, and this kind of integral equation with the singularity less than 1, we can prove existence and uniqueness as with the theory of, and using the method approximation, we can write our solution. We are resolvent this kind of. And we can find the tau and nu for odd k also, and we can construct our solution from the hyperbolic and from the parabolic part same. And say in this kind we can prove existence of our results, existence of the formulating problem of treatment. And We are using it here in some of the results. And at the moment, we are working this kind of integral-differential equation, Laudot equations, second order, and also for the third order, second and third order, this kind of Laudot integral-differential equation, formulating boundary value problems, type of problem of trichomy, and type of problem of Gillerstedt, and we are investigating existent in humans this kind of boundary value problems. Thank you very much.